Welcome back. I'm here to re-record the lecture that I did at the end of class yesterday on Thursday on Zoom, since I wasn't able to record it with my little laptop streaming and chugging along with Zoom. So I will do it separately, as I promised. Here we go. We didn't get very far, and I will likely go back over this at the beginning of Tuesday's class, so this will be a quick overview of what you missed. So we talked about the idea of a generalized linear model having three main parts. The part in red here, number 3, is actually the same as usual. The new parts relative to what you're used to thinking about in a regression framework are 1 and 2. So first, we have to decide what the conditional distribution for our outcome y should be, where the word conditional means after adjusting for all of the model predictors. So the leftover part, we would call that the residuals. In general linear models, we say that the residuals are supposed to follow a normal distribution, which means that there is a separately estimated amount of variance in the outcome, and it is assumed to be constant because that's what the normal distribution specifies, that it is indeed constant across observations. Well, that's not going to work or be plausible for many different types of outcomes. So we will pick a different distribution that better matches the possible values of the outcomes instead. For instance, the first thing that we'll talk about is binary variables, which are going to be characterized by a Bernoulli conditional distribution. Likewise, counts may be characterized by a Poisson, and what's notable about these is that there is no separately estimated variance, and it must be non-constant because it varies as a function of the predicted mean. Why does this matter? Because the model for the variance is used in computing the standard errors of the fixed effects, and the standard errors are used in computing the test statistics and their p-values. So it's the inferences about the effects of our predictors that could be off if the distribution that we choose for the outcome is not an appropriate one. By the way, for those of you who are in the multi-level models classes, if you've heard of random effects, in the Agresti textbook that I assigned for this class, he refers to this idea of a conditional distribution as the random component. That is not a synonym for random effects, so don't get confused. The second part that's new is known as a link function, and that is a transformation, but it is not a transformation of the data, it is a transformation of the conditional mean to be predicted, so like y hat essentially. And the object is to create a conditional mean to be predicted that is unbounded. That way we can throw our regular linear model slopes at it. So link means going from the original outcome to this continuous unbounded version to be predicted. To go backwards, back to the data, it's known as an inverse link. So what happens is that the model predicts some outcome. When you back translate it into what the actual outcome scale would be, the predicted outcomes then stay within bounds. So for instance, if I'm talking about a binary outcome, the conditional mean to be predicted is the probability of a 1. So what the link function will do is create an outcome that's continuous, and when it's back translated into a predicted probability, it will stay between 0 and 1 as it needs to. Likewise, for count outcomes, then we have a boundary at the 0 side only, so the link function that we would choose is usually the log. That way, predicted counts can go as high as they need to, but the smallest the predicted count could ever be is bounded at 0. It'll stay above 0. And in the view of general linear models being a subset of these generalized linear models, the way that that works is if you say that general linear models use what's known as an identity link function, which means no transformation, just multiply it by 1. So I gave you a real-life example of a bummer of an identity link as a multiplier. So this is a scratch-off ticket, which I scratched off on Christmas morning, as we do in our family. This was from the year that we were in South Carolina in Hilton Head for Christmas. And this is a bingo ticket where you have the numbers and letters here, and then you have to scratch off on your card if you have these numbers. Well, I got a bingo right here, and it said over here that I won $10. But this is not just bingo, this is bingo extra. So you also get to scratch off a multiplier, and as it says on the card, multiply up to 5 times. Well, my multiplier was 1. Wah, wah. So I call this a real-life bummer of an identity link because my winnings were only multiplied by 1, not really transformed after all. Once we have a different conditional distribution that better matches the possible values of the outcome, and once we have figured out how to take the outcome and turn its conditional mean into something continuous through a link function, then we're ready to use what's known as a linear predictor, or what you would probably just call the model. And I note that this is composed of any fixed effects as well as random effects in multi-level versions of these models. The good news is that everything works like you're used to at this point. You just have to keep in mind that what is being predicted is not the original outcome, but the link transformed version. So we're not predicting the probability of a 1, we're predicting, say, the logit of the probability. We're not predicting the count, we're predicting the log of the count, that kind of idea. But then we can use our familiar 1 unit change language to talk about, for every unit change in x, logit y or log y goes up by this much, and everything works just the same. In terms of estimation, though, you can run into problems in models that have a lot of predictors, because now all of the fixed effects have to get searched for through the same iterative likelihood maximization process. So the idea of finding the parameters that make the data jointly the tallest, that has to happen for the fixed effects as well as any variance-related terms. So what would happen, for instance, if we tried to predict a binary outcome using a traditional general linear model? In that case, if we think about what the outcome mean would be, right, if you don't know anything else about a person, the best guess for their outcome is the mean. That's still true for binary data, but it means the probability of a 1, or the proportion of a 1. So that's what we're going to be predicting in a general linear model if we don't do anything different. So beta 0 would be the intercept, the probability of a 1 when all the predictors are 0. The slopes here would be the change in the probability of a 1 for a 1 unit change in x. And then e would be the difference in between 0 and 1 that you actually got and whatever your predicted probability is. So what could go wrong? Well, number 1 is going out of bounds. Probability is bounded between 0 and 1. So if we throw a linear predictor in here, like a linear slope for the effect of x, what can happen is, say, for an x of 11 in this prediction, we have a probability of 1.2. So you're really whatever that 1 means. And over here we'd have a probability of negative 0.2. So this doesn't make any sense. What we need is a model that understands that we can't go out of bounds in terms of the predicted probabilities. So we need a slope that shuts off as it approaches those boundaries, or it asymptotes, so to speak. So it translates into a nonlinear function of x predicting probability. The way that we do that is our new best friend, the logit. So step 1 is to convert probability into a quantity known as odds. So it's the probability of a 1 over the probability of a 0. And even though this is indeed a ratio, this is not an odds ratio. This is just odds. It's a source of confusion. So if I have a probability of a 1 of 0.7, that means 0.7 divided by 0.3 gives me an odds of 2.33. But if I go backwards, if I have a probability of 0.3 divided by 0.7, then odds is 0.4. So the scale of odds is weird because it's unbounded on the positive side, but it's still bounded at 0. So some genius figured out how to fix the lower boundary by taking the natural log of this odds, and that gives us what we call the logit, or the log odds. So as I said in class, I once had a student argue with me that it shouldn't be logit because you take the log, it should be the logit. I don't think that's wrong. So you can call this a logit, or a logit, or a log odds. But the idea then is that you've created a metric that is continuous and unbounded on both sides, and it's symmetric at 0. So if I have a probability of 0.5, so 0.5 in the numerator, that means 0.5 in the denominator, that ratio would be 1. The log of a 1 is 0. So 0 in logits corresponds to 50-50 probability. Here's the correspondence between probability on the y-axis and logits on the x-axis, and they are super helpful to interpret both positive and negative amounts vary from 0 to the same amount. So what I'm saying is, like if I have a probability of 50-50, 0.5, that's a logit of 0. Okay, so that's where neutral is on this scale. If I have a probability of 0.9, so that's 0.9 divided by 0.1, take the log of that, that works out to be a logit of 2.2. So the opposite, if I had a probability of 0.1, would result in a logit that's the same size, just with a negative. So this symmetry means that I know what the logit would be regardless of whether I'm talking about the probability of a 1 or the 0. And I had said, I'll let you go in class if you can tell me the answer to this. If I have a probability of 0.99, that corresponds to a logit of 4.6. What would it be if I had a probability of 0.01 instead? The answer, negative 4.6, because it's just minus 1 times whatever the value is. And we didn't get to this slide yet, so I'm not going to either. By the way, if you're thinking, is this logistic regression that she's talking about? Yes, that's exactly what I'm talking about. I'm presenting it from a perspective of the pieces or the ingredients that make it a logistic regression, because if you recognize the pieces, then you can switch them in and out to make different kinds of models for different kinds of outcomes. So a logistic regression uses a logit link function, and it uses a Bernoulli conditional distribution, which we will talk about next week. So thanks for being here. I will see you on the other side.